Oftentimes, experimental science can be a bit different from theoretical science. And in order to ensure that our process is less complicated, we like to simplify it by focusing on that which is relevant to us. So that brings us to the concept of systems. A system in physics is a way to narrow down the parameters to focus only on that which is relevant to the situation that's being observed. For example, if you're doing an experiment in a lab, then your system will probably be the apparatus that you use. For example, for your chemistry experiment, it could be a few test tubes that you're observing. And if you're trying to observe the law of gravitation, you are more likely to focus or observe the behavior of different planets. So your vision or your viewpoint of different things changes depending upon what you're trying to deduce from your observation. So a system is the parameter of our observation. Now, a system can be as large as an entire planet, as I mentioned, or it could be as small as an apple. Okay? Let's say you have an apple sitting on a table, and that apple continues to stay in its state, like its current state, which is it's stationary. So that brings us to the concept of equilibrium. Remember that when something follows Newton's first law of motion, we can say that it's an equilibrium. Now, what's Newton's first law of motion? It states that if something's stationary, it continues to stay stationary until an external force acts upon it. Or if something's moving, it continues to move until an external force acts upon it. Now, that external force can be you trying to lift the apple off the table, okay? And that would change its state. It was sitting on a table, stationary, but you could provide it a little push and it would start rolling down the table. Okay, so what is equilibrium? Equilibrium is when something stays in its state, like its current state, and nothing happens and nothing changes. Okay, equilibrium could also be referred to as no change in the current state. Now, if I were to remove the table somehow, what would happen? The apple would fall, right? Since there is a change in our system, what was our system? Our system was simply the things that we're observing. We're observing the table and an apple. Now, since the table disappears and there is a change in our system, things happen. And when things happen, energy is transferred. Okay? So, when you remove the table, the apple falls. It changes its state of being stationary. Okay? It starts moving. And when there is a change in our system, energy is transferred. And in the following class, we'll see the different types of energy and how energy is transferred from one object to another. Okay? So we learned that when there is a change in system, energy is transferred. And that change in system also portrays that the object is no longer in equilibrium. Energy is a very interesting topic. It's simply the ability or the capacity of something to do work. Simple example, you wake up in the morning, you have breakfast, and that gives you energy to do work for the rest of your day. Now, we have different types of systems. Before we learn about the types of systems, we need to know what is matter. Matter has two characteristics. Anything that has a certain amount of mass and that occupies space is referred to as matter. And we know that there are three states of matter, the ones that we discuss in this course: solids, liquids, and gases. We know that all of these states have a certain amount of mass and they occupy space. Let's take an example of a solid. Your pencil, it has a mass and it occupies space. Your glass of water, the water in the glass has a certain amount of mass and it occupies space. Gas particles, like air in your room, it does have some mass and it occupies space. The mass is very negligible. That's why you're not feeling it on yourself. But if you started running, you would feel those air particles against yourself and you would know that they definitely have some mass. That's why you're feeling them in the first place. And they're occupying the room that you're sitting in. So matter is anything that has mass and occupies space. Now, the types of systems that we have here are three. First one is an open system. Secondly, we have a closed system. And thirdly, we have an isolated system, and that's the one that we usually refer to. So, a closed system is the one in which energy and matter are allowed to be exchanged with the surrounding. Okay? So, this is your system. This is your area of observation. Okay? And the rest of it is referred to as the surrounding. A system in which energy and matter can be exchanged with the surroundings, which means it can enter or leave the system, is referred to as an open system. A system in which only energy can be exchanged but no matter leaves the system is referred to as a closed system. And a system in which neither energy nor matter leaves the system is referred to as an isolated system. Let's take real-life examples to understand these systems. If you're doing an experiment and the experiment involves a test tube, okay? If the test tube does not have a lid and this is the room in which you're observing your experiment, then this is an open system. Let's say one of the products of your experiment is a gas, and that gas leaves the test tube in the form of vapors. So matter is leaving the test tube. I'm representing it with green. On the other hand, heat is also dissipating from the test tube and energy is leaving the test tube, which is your system. If you took the same test tube, but you put a lid on the test tube, that would prevent vapors to leave the test tube, so no more matter can leave the system. Okay? However, energy continues to leave the test tube as in the form of heat. That is your closed system. Now, if you were to take your test tube and let's say put it in a box here, okay? No more heat can leave the box. So you've defined a new system, which is this new box, and no more heat can leave the box. And now neither matter nor energy is leaving the system, and that's an isolated system. Okay? And this is what we use for ideal conditions in which we like to perform our experiments. It might not be practical all the time, but we would refer to this for ideal laws. Now that we have a solid understanding of what a system is, we can move on to the concept of energy. Energy is the capacity to do work. I like to imagine energy as objects having stores of energy, okay? For example, we know that energy is stored in objects. And when there is a change within a system, that energy is transferred between objects or between stores, okay? So if you have a plant and that plant has made some food using the process of photosynthesis, which is a chemical reaction, then that plant has a store of chemical energy. I'm using, let's say, white to represent a store. So this is simply a store of chemical energy. Chemical energy. Now, when a human consumes the plant or an animal consumes a plant, that energy is transferred to a human. Okay? So that store is transferred from the plant to the human because the human consumed the plant. See? So that is a transfer of your chemical energy store. Now, there is this one important law referred to as the law of conservation of energy. The law of conservation of energy states that energy cannot be created or destroyed. It can only be transferred from one store to another. Basically, it means that you can't create energy out of nowhere or you can't destroy energy. It can only be transferred from one object to another or from one store to another. Okay? This means that in a closed system, where no matter leaves the system, the total amount of energy is constant. Okay? We have different types of energy as well. First of all, we have kinetic energy. Kinetic energy is the energy of motion. When something starts moving, it gains kinetic energy. Okay? So, energy of motion. To understand gravitational potential energy, we need to have a basic foundation of a few concepts. Any mass, let's take the example of a planet, Earth. Let's say this is our planet Earth. All masses have the ability to attract other masses towards themselves. Okay? Even you and I, being masses, have the ability to attract other masses around ourselves towards ourselves. But since our mass is comparatively too small, we can't physically attract things. But since the mass of the Earth is huge, it's able to attract other things towards itself. But that attraction is limited to a certain area. The area in which the Earth is able to attract other masses towards itself is referred to as the gravitational field. First of all, remember that that attraction is gravity. and the direction is towards the center of the mass. And the area surrounding the mass in which the mass is able to attract other objects toward itself is referred to as the gravitational field of the planet. So this blue region is the gravitational field. For example, when you're playing football, you play in a field. You can't go outside the field. Likewise, the Earth is attracting other objects towards itself in a certain amount of field. It can't attract things outside of that field towards itself. Let's say there is a comet going past the Earth, and it happens to enter the gravitational field of the planet. Now, as soon as it enters the gravitational field of the planet, it will be attracted towards the planet and it will crash on the Earth. Okay? So, gravity is the attractive force of the planet, and the field is the region around the planet in which it's able to attract things towards itself. Now, when an object is on the ground, let's say here, let's say we have a object on the ground. Then in that position, it's stable, right? Like if something's already on the ground, where would it fall, right? But when you raise that object above the ground, okay, now it has the capacity to fall, okay, because the gravity is attracting it towards the ground. So it gains a form of energy that is referred to as the gravitational potential energy. Objects gain energy in their gravitational potential store when they're lifted through a gravitational field, because now they have the potential to fall down, and that falling is referred to as work. And going back to the definition of energy, it's simply the ability to perform work. So when you raise an object above the ground, it has some ability to fall towards the ground, and that is gravitational potential energy. So gravitational potential energy is energy objects gain due to their change in position, okay? Okay, when something falls, okay, first of all, you raise something, right? Let's say you have, let's say this is the ground, and you have a ball here. When you raise the ball above the ground, the ball gains gravitational potential energy. But when you let the ball go, it falls down. When it falls down, it starts motion, right? And when it starts moving, that gravitational potential energy is converted to kinetic energy, okay? Because kinetic energy is the energy of motion. So remember this conversion of energy. Gravitational potential energy is converted to kinetic energy. Next, we have elastic potential energy. This energy is usually stored in elastic objects like springs and rubber bands. Now, if you have a spring, let's say this is the original length of the spring. If you stretch the spring, okay, let's say that the spring is attached to a fixed position on one end. It's attached to a fixed position on one end, okay, here. Now you apply a force and you stretch the spring. and you see an extension in the length of the spring. You're holding the spring for now. When you let it go, it goes back to its original position, which is this one, right? When you stretch the spring, it gains some form of energy, which is referred to as elastic potential energy. Now, the spring has the potential to go back to its original position and do some work. So, whenever you stretch something that is flexible, let's say, then it gains that ability to do some work and go back to its original position. So, that is elastic potential energy. If you have a rubber band, here it's loose, right? It doesn't have any energy right now. Remember, when something is loose, it does not have elastic potential energy. But when you stretch it, okay, you are stretching it for now, and when you let it go, it will try to come back to its original position, which is this one, and it can only do that by doing some work. And that potential to do work is referred to as elastic potential energy. Okay? All right. Next, we have magnetic energy. We all have played with magnets at one point of our life or another, and we know that we have the North Pole and the South Pole. Just like planets, magnets also have a field around themselves in which they can apply a force on another magnet. Okay, here. So this is a field in which the magnet can attract or repel another magnet. Remember that unlike poles, attract and like poles repel. If you have a magnet, let's say at this distance, nothing happens, and you bring it closer and closer and closer, and immediately and suddenly you see that when you reach a certain distance, you don't have to apply force any longer. The magnet snaps and gets attracted to the opposite magnet by itself. And if you had the opposite situation, which was that unlike poles were in front of one another, you would bring the magnets closer and closer and you would try to um, make them touch each other, but at a certain distance, when they both cross each other's magnetic field, no matter how much force you apply, they won't come into contact because this is the region in which that repulsive force is being applied by both the magnets. So a magnetic energy is stored in magnetic materials that are interacting with one another, okay? And they it's just the ability for magnets to either attract or repel one another, okay? So magnetic energy is the energy stored in magnets. Next, we have the story of charges. Let's go back to the basics. We know that everything is made up of atoms, right? What's an atom? It's a particle that has the same number of electrons and protons. Let's say we have the nucleus here and an imaginary shell surrounding the nucleus in which electrons orbit. the nucleus. Okay, so in the nucleus we have two protons and remember protons are positive and two neutral neutrons. Neutrons are neutral. And surrounding or orbiting the nucleus are two negative electrons. This is an atom. The number of positive charges, which are protons, is equal to the number of negative charges, which are electrons. Now, the positive charge cancels the negative charge, leaving an overall charge of 0. So the atom is neutral. Okay? Let's take another example instead. Let's say we have 3 protons and we have another shell. And in the second shell you have 1 electron. Now you have 3 negative charges and 3 positive charges. Everything in the universe wants to be stable, and we know that noble gases are stable. Other than the noble gases, we have helium, which is stable, which has 2 electrons in its last shell. Now, this atom also wants to attain that stability. The only way that it can attain that stability is to either lose this 1 electron or gain 7 more electrons to have 8 electrons in its last shell. It's easier to lose 1 electron than to gain 7 more electrons, right? So this atom loses this electron. When the atom loses an electron, what we're left with is this structure here. Two electrons in the first shell, and the second shell is no more there. Now, you would see that in this situation, we have 3 positive charges and 2 negative charges, and they're not equal. 1 positive charge cancels out 1 negative charge. Second positive charge cancels the second negative charge, but we have an additional positive charge. So there's an overall plus charge on this particle, and since it's not neutral anymore, we can't call it an atom, we call it an ion. And it's a positive ion. Okay? That was the background story here. That was the background of how charges are formed. Now, when you have charges, let's say a positive charge and a negative charge, these charges have the capacity to attract each other. Remember, unlike charges attract, and like charges or same charges repel each other. So this charge also has an area around itself in which it can attract or repel another charge. And when these charges encounter the electric field, that area is called the electric field, okay? So when these charges encounter the electric field of one another, they will attract each other and come closer. But if we had like charges, let's say 2 negative charges, they would repel each other as soon as they encountered each other's electric field. So electrostatic energy is the energy stored in electric charges, which gives them the capacity or ability to either attract or repel one another once they encounter each other's electric field. Okay, next we have chemical energy. So, chemical energy is an energy um, transferred by chemical reactions. So, whenever there is a chemical reaction involved, you have chemical energy that is being formed. Not formed, but transferred. No, sorry, دوباره chemical energy. Chemical energy is the energy um, transferred as a result of chemical reactions. For example, plants use the light energy and convert it or transfer it into the form of chemical energy by the process of photosynthesis, which is a chemical reaction. Okay? Most of the times, when batteries are involved or food is involved, there's chemical reactions being carried out in them. So that at that point, we're referring to chemical energy. Next, we have nuclear energy. Whenever there is a nuclear reaction in which the nuclei of atoms release energy, that energy is referred to as nuclear energy. And lastly, we have thermal energy. Thermal energy is simply the amount of heat that an object retains. And the hotter the object, the more thermal energy it stores. So thermal energy in very simplified terms can be referred to as the amount of heat in an object. Now, once we know the types of energy, it's important that we learn about the pathways via which energy is transferred. We have four important energy transfer pathways. The first one we have here is mechanical work. Whenever a force acts on an object, for example, by pulling, pushing, stretching, or squashing something, we say that energy is transferred by the mechanical pathway. Whenever we have a charge whose movement is involved through a potential difference, then that form of work is electrical work, or that form of energy transfer is by electrical pathway. So we know that the concept of potential difference, we'll learn more about it in detail in the other section, but let me just give you a brief idea. If you have two sites and one of them has 9 volts potential and the other has, let's say, 8 volts potential, or let's do 4 volts potential, then the charge will move from higher to lower potential. So when you have a charge moving through a potential difference, that's your electrical pathway. And remember, movement of charge is referred to as current. What's current? Current is simply a moving charge. When you have a static charge, it's electrostatic. No, no. When you have a stationary charge, that's simply a static charge. But when you have a moving charge, that is referred to as current. I will use the letter capital Q to represent charge. Charge moving through a potential difference. See, there is a difference in this potential. Here we have 9 volts and here we have 4 volts. So this is referred to as potential difference. And whenever you have a potential difference, the positive test charge moves from higher to lower potential. Next, we have heating by particles. In this pathway, energy is transferred from a hotter object to a colder one by movement of particles in that object. And heat is transferred from hotter to colder object. And then we have radiation, heating by radiation. Energy that is transferred by EM waves or electromagnetic waves is referred to as heating by radiation. That's one form of pathway by which energy is transferred. For example, visible light towards sunlight is transferred. It comes to the planet Earth in the form of an EM wave, and that energy is used by plants to carry out the process of photosynthesis and form chemical energy. So a few months ago, I went to one of these Star Night events by the Royal Astronomical Society of Canada, and there were these really cool professors and amateur astronomers who came with their telescopes, and we were all supposed to see the sky, the night sky, and view a few planets as well. But the weather wasn't the best that night, and we weren't able to view anything. And on top of that, I forgot my gloves at home. My hands were freezing, and there happened to be this coffee stall, not coffee, it was hot chocolate on the side. Even though I'm not the biggest fan of hot chocolate, I grabbed a cup. And let's talk about heating by particles from that story. So, if you see here, the system is the hot chocolate, the mug, and my hand. Okay? Because that's what we're observing right now. Now, that hot hot chocolate saved me that night by warming my hands. How did that happen? That happened by energy transfer. Energy was transferred by the process of heating from the thermal store of the hot chocolate to the thermal store of the mug. Okay? So, first of all, energy transferred from hot chocolate to the mug. Okay? And then energy was transferred by heating from the mug to my hands, warming them up. All right? And how did that happen? That happened by particles. Okay? The particles in the hot chocolate were vibrating, and by vibrations, they transferred their heat to the mug. And then the particles in the mug were vibrating, and they transferred that heat to my hands, saving me that night from going home early and missing out on nothing. Anyways. All right, let's take an example here and see if we can identify the energy transfer pathways and the forms of energy that are being transferred in these examples. The first example here is a battery powering a bulb. First of all, we need to determine what form of energy is transferred to which form, okay? When you have a battery powering a bulb, the setup would look something like this. You have a battery here, and you have a few wires, and you have a bulb, okay? And you're likely to have a switch as well. So when you close the circuit, when you turn the switch on, when you close the circuit, the chemical reactions happen in the battery and the charge flows through the bulb as a result of that. So we can say that energy is transferred from the chemical store of the battery to the thermal store of the bulb, okay? And how does it happen? It happens by movement of charge. And when we have movement of charge, the pathway is electrical pathway. Okay? I'll repeat that for you. For a battery powering a bulb, our system is the battery and the bulb. Okay? So the energy is transferred from the battery to the bulb. In the battery, we have chemical reactions being carried out, and those chemical reactions have chemical energy. And in the bulb, you have heat dissipating from the bulb or light dissipating from the bulb, okay? So when the circuit is closed, the bulb lights up, okay? And so energy is transferred to the thermal store of the bulb. Energy is transferred from the bulb to the surrounding as a form of light, but this is not described in the parameters of our system since we're focusing on the bulb and the battery itself and not what's being released to to the surroundings. So we can say that energy is transferred by the flow of charge around the circuit, and so the pathway is electrical. We have chemical energy transferred to thermal energy by electrical pathway. Second example here is a ball falling towards the ground. We've discussed this briefly earlier as well. Let's look at this again. Here is a ball and it's falling towards the ground. So a ball can only fall if it's been already raised above the ground. So when it's above the ground, it has gravitational potential energy. And when it falls, it starts moving. And that gravitational potential energy is hence converted to kinetic energy. Okay? And how does this happen? A force is being applied to the ball, the force of gravity. So it's mechanical pathway. I hope you can identify the types of energy transfers and the pathways now. Don't worry too much about the parameters, they're only there to help you visualize what you're observing in order to save your time.